So here's the fifth and last video for class 1 in fluid mechanics, and we're just going to cover a couple things that are interesting and important. Starting out, so I just wanted to be thorough. I don't know if I'll do this with every chapter, but I did in this chapter. We're going to talk about modeling in engineering, and the first thing that comes to my mind is Monty Python and Holy Grail. Well, they're looking at Camelot, and everyone dances around, and one of the guys says, "It's only a model." Well, okay, so it's just a model. But what we mean by modeling, we try to make some kind of representation of the real world, and we have to simplify it to be able to accomplish a task, right? And I'm not going to read these slides to you. I will mention that one of the cornerstones for us in science and in engineering is the differential equation. We won't be doing a lot of differential equations, but we need to think about them and look at them and see how important they are in in coming up with equations that we commonly use, right? And when we do that, we create boundary conditions as part of that simplification. It's necessary, and therefore the equations that result always have limitations and how we use them. So we have to be really careful not to be just plugging and chugging of numbers into equations. We need to know where they came from. So that's one of the reasons why that we will definitely hammer home how we derive many different equations. We don't want to just overlook it and turn our brains off, but we want to keep in mind where they came from, so you can see what the assumptions were and the boundary conditions and the limitations, because we have to simplify things in order to accomplish to find the goal that we want. And sometimes something might be way more complicated than can be solved with a simple equation. Even though you might see all the parameters that you know equals the thing you want to get, you can't just shove numbers into any old equation. It is a big trap. So I want to mention they have a section in here on problem solving technique, and they're quite formal in what they're putting through here, but I want to instead go to not instruction information. There's my picture right there. I want to go to course information and come down and talk about my requirements for homework. All right. So I want you to use engineering paper, or if you don't want to buy it, it's not that expensive. I think for like $10 you get like 200 sheets. That's a lot of paper, and it'll last you not in just this class, but like every class. I don't think you'll need to use 200 pages. Hope not for homework here. But I want you to be very neat and put down enough on the page so that another engineer could figure out what you're doing, or more importantly, what you can read your own work later on and figure out what you did to get the answer. It's really important to document your work as an engineer and to be as thorough and organized as you possibly can. So just recognize that different choices that you have here. So you could go get some engineering paper, or you could do this simulated paper right here. So there's a PDF, and you could just print this out and do your work on there and scan it, and I'd never know anyway, so I don't even care. But you could save maybe a couple bucks. I don't know. You could do the math and find out if the page per print it costs how much. Or you could do it electronically if you really want to. If you have a well, you could do that with an iPad or anything. Like I have a Microsoft Surface book that I use a lot. But you can. I also have it in Word if you want. So what you could do is you could paste the problem statement up in here. Oops, I actually put ES211. It should have R. So when you go to do when you go to do this, maybe I need to update this right here. Go double click into the margin. Go ME 340, and you can put your homework in and put your name in there. But you could go to the assignment PDF and clip and paste it and put it in there. You don't have to write out the entire problem, but I want the diagram, just a little bit of a diagram, and I want you to use a straight edge for this, and give me the givens and the find, and I want the diagrams. Don't skip steps. Use plenty of paper. The paper isn't that expensive. Most of the time I want one problem per page. I think in this first homework assignment I've made some exceptions because they're very, very short. A couple of them very short problems. You can fit more than one on one page, but don't try to cram it on there. I see a lot of students that really get stuck on doing their homework because they've tried to see how much they can cram into one space. And I really want you to rewrite your answer at the bottom and box it, please, so I know exactly. Make sure you use the correct units, and do not use less than 3 and no more than 4 sig figs. I really would like this to be neat and for you to be consistent with it. Really important. This Dr. Dave Mazurek, who is an author of our dynamics, or actually the statics book. Here, I'll show you. Mazurek, right here. He's teaches at the Coast Guard Academy. Really great guy. He was my he worked in the office next to mine for at least one semester. Maybe it was more than a year. Anyway, I sat through his mechanics and materials class, and he said what I thought was very profound, and it was like organized work leads to organized thought. And I think that's really important. If you're really confused, Dave M. If you're confused by a problem, by being organized can really help you try to tame the chaos that's going on in your head and try to get to a solution. But also, just in terms of documenting your work, it's really important because the enemy of the engineer is the lawyer, right? We're trying to make the public safe by designing or analyzing or troubleshooting, solving problems to keep the public safe. But sometimes it doesn't work out, and lawyers will come and get involved, and you're going to need to show your documentation, and it better be neat, because you can only picture yourself on the witness stand trying to explain your chicken scratch, and you can't even remember what it was that you did. So, engineering paper, write down the problem statement, make a drawing of the thing. You don't have to always do assumptions, approximations, unless you did some. You don't always have to write the physical laws, but usually the main equations are what we were talking about. Write some of the properties down. Just kind of summarize the thing or the things that you looked up, and show all your calculations. Don't skip steps. And then at the end, you might want to write a little bit like this, or show the dimensionally homogeneous. Therefore, it looks like I think, I have this much confidence in what I did, right? But something along these lines will really look like, so let me see. This is a long problem. Okay, so here's a problem that I did in mechanical design last fall, right here, okay. So it was to design this hanger conveyor, right? I have my name and everything up here. I made a drawing of the problem. I had the load was varied from 600 to 3,800 pounds. I wanted to design for a safety factor of 2. I do my shear moment diagram right here with an FBD on the top of it. And I find my reaction forces. I find what my moment is, what the maximum and minimum moment is going to be based on this force changing. I get my alternating and mid-range moment. I have my material. I should have written down where I got this from. A mistake I should have made, but not perfect. Going through some of the calculations. I should maybe even write down what equation I used right here. That would have been a good thing to do. I find a section shape that's going to mix. I designate what it is and what its section modulus is, that it's larger than the minimum required here. And I can have my material and my the section. So what I've done is I've designed this bracket. I've designed this hanger. I've picked out a cross section that I believe will work for the design. Same thing, I have designed a crank right here. It tells you that this angle right here is 45. You get the idea, right? This this looks neat, and it communicates to another engineer that's familiar with this method right here, what has been done and what decisions were made, how this came about, and here's my final design, right? What the thing looks like, and hopefully somebody could build it from that. So I'm just trying to show you what my expectations, and hopefully sell you on the importance of them. I'll talk a little bit about engineering software packages. We're going to do a little bit of a project in this course. Using a CFD, which is Computational Fluid Dynamics. And we have kind of three that we could possibly use here at the University of Hartford. COMSOL, Fluent, I believe we have that available, but we also have SolidWorks Flow Simulation, and I'm a little more familiar with that. But here's like a little bit, I mentioned the Navier-Stokes equations. Don't be intimidated by them. It's just a bunch of shorthand. We're just talking about a balance of forces, and here's viscous forces, and no, these are inertial forces. We should also have viscous forces, we have pressure forces, and body forces, but from this we're able to get velocity and pressure related to each other. Pressure and flow. This is too difficult to solve by hand, so we often will do it numerically, and that's what computational fluid dynamics is all about. And we usually generate these pretty pictures to kind of try to show us what the velocity distribution is, or what the pressure distribution. Here's the velocity magnitude, is what the scale is of these pretty pictures. So you can see the interactions between this propeller and the hull and the rudder. Or we might have, here you go, here's a drone, right? Trying to figure out what the flow, so these are like streamlines, and the magnitudes are represented by the colors. Or here's an impeller and a pump. Or here is blades that are going around in like a turbine, like it could be a gas turbine or a compressor in a gas turbine. Flow going around the body of a helicopter. Or we can see the pressures on the bodies, but also the flow streams and turbulence that are taking place around a race car, or maybe inside an engine, the flow inside the intake or exhaust. Here's pressures around a ship hull, and here's the wake that's being formed on a ship, and here is really important. The flow around a cow, and someone might want to know that for some reason. Anyway, here's a real world. At my old job, years and years ago, we hired somebody. Well, first off, we were tasked with trying to figure out a way to stop this exhaust from recirculating back into what they call it the house. That's where people live on a ship, right? So the exhaust was recirculating because of some airflow. So when the ship's speed and the wind speed, so the relative speed, was a certain way, was just the right way or the wrong way, if you want to think of it that way, the exhaust would come back in and people would have to breathe it, and that's no good. So we decided to hire a subcontractor, because we didn't have that software in-house, to take a look and simulate what was going on, so we could kind of try to see, can we quantify what's actually happening. And so this was some of the results that they came in, and what they found was that this bridge wing right here appeared to be the thing that was causing this flow, and the vortices were kind of the patterns were sufficient, and when the exhaust was kind of like not rising up high enough because the ship was going too fast, they demonstrated that they could recirculate back into this intake plenum. And I think, this is still showing some of this. So we had a bunch of different solutions proposed. Some of them were to put little foil shapes onto the bridge, but we decided that the best way to go about this was to actually put a nozzle that can be adjusted onto the exhaust. here, and it did create some restriction, some amount of restriction, which is not really necessarily good for the engine, but we quantified, estimated what we believed the increase, and we checked, and the turbocharger manufacturer, it was within their parameters allowable back pressure. So by doing so, we increased the velocity coming out of the stack, and we shot up the exhaust up higher in the air, and therefore we were able to avoid this recirculation. Here's some demonstration. Okay, so I use SolidWorks flow simulation. This is like years ago, so I think it's a lot easier to do. But I didn't know what I was doing, and I just followed a tutorial, and then I was able to replicate, or I tried to replicate, attempted to. So a very standard thing using increasing Reynolds numbers. You can see this diagram down here at the bottom. This is the drag coefficient versus Reynolds number. Right? Drag coefficient is non-dimensional, Reynolds number is non-dimensional. So I picked out some parameters for my fluid, and I made sure that the flow was a Reynolds number of 1, and that's based on the far field velocity, the velocity way out in front of the thing. Here's like little pictures of that correspond on this graph with here's A and B, C, D, and so forth. And I tried to get kind of close, so you can kind of see here's a Reynolds number of 1, 10 to the 0, right in there. So I have this kind of it's pretty close to A. And then it gets to 10, so you can see it's kind of close to B, and you can start to see some things changing, and then you can start to see some of the flow changing some more, right? So this is getting closer to C. I think this next one is much closer, yeah. So now you're seeing, this is a CFD simulation. This was empirical data over here, and you can see that we're capturing that. And this scale is changing, by the way, with every proportionally. You can see with these, so you kind of see that this. There's lots of different features that we could start talking about here that you're not aware of yet. But this was not difficult to do, so that's going to be what our project is going to look like. We can start trying to learn that. All right, so I've already exceeded my 15 minutes. I wanted to briefly talk about the difference between accuracy, precision, and significant digits. I really want to hammer home. I want you to use at least 4 significant figures in your answer. At least 4 significant figures when you're doing calculations. Don't round down early. Don't wait until the very end to round if you're going to round, and then don't give me any less than 3 sig figs in the answer, and no more than 4 sig figs. So 3 to 4. Don't give me 5. Don't give me 2. Don't give me 10, because increased number of significant digits implies a greater certainty, and we don't have that high degree of certainty, so we don't want to give too many sig figs in an answer, right? So you can see this is a classic thing where you can see here's accuracy or inaccuracy. You can see that it's not in the bullseye, but I have the nice grouping, right? So I guess that means that this is I'm sorry, I have to read this again. I get these confused all the time. The value of one reading minus the true value. The value of one reading minus the true value. In general, accuracy of a set of measurements refers to the closeness of the average. Okay. See, that always gets me bad. I would have thought the other way around. Boy, words are hard. So, shooter A is more precise, whereas shooter B is more accurate. That's what I thought. Boy, they get me confused on these. But anyway, there's some examples to go back in here. But this is the one that I liked, but most of the one I kept in my notes. And I said, all right, here's the actual answer. And here's 2 sig figs and 2 sig figs. And this one's going to be more accurate. Whereas this one is very precise with 5 sig figs, but this is actually a better answer. And this one is precise and accurate, but I think 5 sig figs is too many. I would only give it 4 sig figs. Maybe even just give it 3 sig figs, but not less and not more, right? And finally, there's this guy down here. I think he's really, really important, because sometimes there's a misunderstanding right here. this right here is only 1 sig fig. Just remember that, okay? These leading zeros don't give you sig figs, whereas trailing, well, I right here, I kind of think personally, okay, so well, this right here is definitely 5 sig figs right here. I think we could argue about these, whether, we don't quite know, but if the answer was something that where these were filled in right there, and then you just left them off, yes, it's 3 sig figs right there. But it could turn out to be that's the correct answer right here. Scientific notation is quite often an easy way to make sure that you're getting the correct number of sig figs, right? So if you just turn it into scientific notation, you'll see whether you have the right number of sig figs. So just be aware of that, and please answer with 3 to 4, no more, no less. All right, and that's it. 20 minutes was too long. Dang. Anyway, we'll record some more videos. Thanks.